Hello, this is Mr. Collier, and today we're going over a probability summative. Okay, so this is a probability task about coin flips, and we're going to first work out the probability of getting two heads when flipping two coins. So one way to do that is we can set up the entire sample space, just heads, 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 tails, tails, heads, and tails, tails. Okay, so probability of getting two heads is going to be simply two heads is 1/4. Okay, so for part B, to get this one, we can again look at the same samples or the sample space for three coin flips. So that's heads, 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 tails, heads, tails, heads, tails, heads, heads. Then there could be tails, tails, heads, tails, heads, tails, heads, tails, 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 tails. There's 8 total possibilities. The probability of two heads equals 3 of those have two heads. This one, this one, and this one. So it is 3 out of 8. Okay, so next find the relationship between the number of coins flipped and the probability of two heads. Alright, so maybe you can't see the pattern yet, so we might need to look at what happens if we got three coin flips. Three coin flips. Well, we need to look at the denominator is going to be looks like powers of 2, so the denominator will be 16. But let's look at two heads. So all the possibilities of two heads are heads, heads, tails, tails, tails. And then let's find the number of ways to arrange this. So we can move this head around like this. We can move the head over one more. And we can move it all the way to the end. Okay, that's all the possibilities starting with H. And then we've got, maybe the first one's the tails. Tails, heads, heads, tails. Tails. Okay, the second one's heads. So let's move this H around. And just writing out all the possibilities here. Okay, so that's all the possibilities. And it could be first two are tails, and then we got heads, heads, tails. So let's move the second one and keep this first heads fixed. Okay, and finally it could be tails, 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 heads, heads. So all together here we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And what have I got written here at the beginning? Sorry. This is actually, I've actually done 5 coin flips, so I've skipped over 4. Anyway, so we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the probability is going to be 10 over 2 to the power of 5 is actually 32. So let's go ahead and do 4 coin flips, which I've totally skipped over. That's going to be heads, heads, tails, tails, heads, tails, tails, heads. And then we can go heads. Oops, I skipped one in the middle. Tails, heads, tails. That's all the possibilities starting with heads. Then we start with tails, heads, heads, tails, tails, heads, tails, heads, or tails, tails, heads, heads. So this is 6. So the probability is 6 over 16. Okay, so let's take a look at that all now in the table. Okay, so we got N, which is the number of coins flipped. Probability here, 1, or actually, yeah, 1. So you get 2 coin flip. To get all two heads, you need to start with 2. So we go 2, 3, 4, 5. We have all these calculated. This is 1 out of 4, 3 out of 8, 6 out of 16, and 10 out of 32. The denominator is obviously going to be just powers of 2. 2 to the power of n is the denominator. The numerator goes in the pattern 1, 3, so let's just write this out. Numerator is going to be 1, 3, 6, 10. You might recognize these as triangular numbers and get the pattern right away. It is quadratic, so we can actually figure it out based on the fact that we know it's quadratic. Okay, so recall, you can write out the general quadratic here as an squared plus bn plus c. And let's fill this in. So if we substitute in 2 for n, we'll get 2 squared equals 4. So 4a plus 2b plus c. Next one is 9a plus 3b plus c. Then we got 16a plus 4b plus c. 25a plus 5b plus c. Then we get the first level differences. Subtract, we get 5a plus b. We get 7a plus b and 9a plus b. Let's get the next level difference is 2a and 2a. It's a constant, meaning it's quadratic. So now we can equate these parts here, for instance. Those should be the same. 1 equals 2a, so a equals half. We've already figured out the a value in our quadratic rule. 2 should be equal to this one, so 2 equals 5a plus b. We already know what a is, so 2 equals 5 over 2 plus b. b equals 2 minus 5 over 2, which is negative half. And now we can go for the c value. This equals that part. So 1 equals 4a plus 2b plus c. 1 equals 4 times half plus 2 times negative half plus c. So 1 equals 2 minus 1 plus c. So actually c equals 0. This means our rule is the probability of getting 2 heads is always going to be, how can we write this? So a value is half n squared minus half b plus, sorry, b we already have, so sorry about that, n I mean, plus c, which is 0. So that's it, and you can write it like this too. We can write that 2 on the denominator and n times n minus 1. So this is the probability of, that's just a numerator, sorry. I should write this as just a numerator. Numerator equals that. So the probability of 2 heads is actually, that's just the numerator. Let's write it as half times n minus 1. Divided by, remember our denominator is 2 to the power of n, right? Which you could simplify if you want to. That's half. We can multiply numerator and denominator by 2. And we get 2 to the power of n plus 1 over here, right? So that's our rule. Now, test your rule works by drawing a sample space or tree diagram. Okay, so let's test for, let's do that in this white space over here, actually. Test for n equals 3, for instance. So for n equals 3, let's draw a tree diagram. HT, 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 and we got HT, HT. Alright, all the probabilities are half. Alright, so that's a lot of writing. Okay, so the probability of 2 heads from the tree diagram is this branch, heads, tails, heads, or this branch right here, heads, heads, tails, or this branch right here, tails, heads, heads. So this is going to be, this one here is, well, half times half times half. This one's half times half times half. This is half times half times half. So we get 1/8 plus 1/8 plus 1/8 equals 3/8. Okay. Now let's check by the rule. By rule we have probability equals, let's substitute in the n, 3 times 3 minus 1 over 2 to the power of 3 plus 1, which equals 6 in the numerator, and in the denominator we get 16, so it is indeed 3/8. So therefore this shows the rule is correct. Okay, so that's it for part 1 of this investigation about coin flips. Let's check out the next part of this investigation, these squares. Okay, find a relationship between the figure number and the probability of picking a shaded square. All right, so let's work out these probabilities first of all. We have 5 out of 9. Okay, you can write that, I suppose, as 5 out of 3 squared if you wish. Next one is, let's count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 out of the total is going to be 5 squared, which is 25, right? And the last one, let's see, is there an efficient way to count here? We got rows of 5. 1, 2, 3, 4. 4 times 5 is 20. So it's like 20 plus 3, 3, 3, 3 times 3, 9. Is that right? It's 9. 4 rows of 5 is 20. Okay. So that's, the total is going to be 7 squared. So it's 29 over 49. Wait, that seems a bit wrong. 4 rows of 4. Oh my goodness, 4 rows of 4. That should be 16. Plus 29 is 25. Okay. So we have those probabilities. The denominator is obviously powers of 2. So the denominator is powers of 2, but it goes 3 squared, 5 squared, 7 squared. So let's do a rule for just those things. In figure 1, 2, 3, we've got 3, 5, 7. The rule for that is, we'll call this length, side length or something. The side length of those squares is always going to be 2n plus 1, because these are increasing by 2. 2n plus 1 matches our table. So we're always going to have 2n minus 1. So the denominator of the whole thing is going to be 2n plus 1 squared. That works for all these numbers. So you get 9, 25, and 49 if you use 2n plus 1 squared. Let's look at the numerator. Let me do that over here in green. So you've got a bunch of rows of 4 here. That's like an m plus 1. You've got a bunch of m plus 1s, right? Okay, so you're going to have, there's n of them in this case. There's n groups of m plus 1. Okay, 4 groups of 3. Oh, there's m plus 1 groups of m plus 1. So it's actually m plus 1 times m plus 1. Then there are 3 groups of 3 here in the third diagram. So that's n groups of n. So it's actually m plus 1 squared plus n squared. The red part makes a 3 by 3 square, and this green part makes a 4 by 4 square in the third diagram. In general, we're going to have n plus 1 times n plus 1 plus n times n, right? So the entire rule for the probability of randomly selecting a shaded square is going to be n plus 1 squared plus n squared. That's just the number of shaded squares divided by the denominator, which is 2n plus 1 squared. Okay, so that is I suppose you can simplify it a bit, but not necessary. Let's verify for part F. Verify our rule with, let's do n equals 4. 41. Okay, we got 41, so the probability of getting shaded equals 41 over the total, which is 9 squared, which is 81. So that's what we should get with the rule. Okay, by rule, we get, remember the rule is n plus 1 squared, so that's 5 squared plus 4 squared over 2n plus 1 squared, which equals 25 plus 16 over 9 squared, which equals 41 over 81. This verifies my rule is correct. Okay. Lastly, let's justify. Okay, G, justify. Okay, so we can draw the general shape. Let's justify with nth diagram. Okay, so let me draw a square like this. The dot 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 to show that there's many squares in between here. Okay, there are always, or wait, let's say a 2n plus 1 by 2n plus 1 square is always formed. Okay, so the total number of squares is 2n plus 1 squared, which is the area of the square, area of the, let's call it the whole grid. Okay, so now let's talk about the rows. And let's do some color coding. Okay. Okay, so let's point out this part. And this is always n plus 1, n plus 1. There are always n plus 1 rows of n plus 1. Okay. And let's draw the other ones in a different color. And n rows of n blocks or squares in between. Okay, so the total number of shaded squares that's supposed to be squares in there is n plus 1 times n plus 1 plus n times n, which equals n plus 1 squared plus n squared. Therefore, the probability of getting a shaded square equals n plus 1 squared plus n squared over 2n plus 1 squared. Okay, so there you go. That's a full justification.